Now, the second part of the example. Okay, so second part, we will be looking at the simple ideal vapor compression refrigeration cycle. Okay, the ideal simple refrigeration cycle. Okay, so that will be based on part B of the questions. We are looking at the same question, so later on you can do a comparison between A, B, C, and D type of vapor compression cycle. Okay, so part B, they say dry saturated vapor delivered to the condenser after isentropic compression in the compressor and no intercooling of the condensed liquid. Okay, we will come into this in the last part. Okay, so when you take a look at this TS diagram, it is slightly different from the previous one. The previous one is a reverse Carnot cycle, okay, where your state point 3 is vertically, or your state point 4 is vertically below state point 3, where it undergoes isentropic expansion for a turbine. But for an ideal, okay, for an ideal vapor compression cycle, state point 3 to 4 here would be irreversible, So that is your thermal, that is where you have your thermal expansion valve, okay? Thermal expansion valve replacing the job of the turbine. We cannot take turbine into consideration, especially for household refrigerator. So that is why we replace it with a very simple component, or smaller component, and much more economical as compared to the turbine. But then, of course, there is a limitation. So you can see here 3 to 4, okay, is actually irreversible. And then that causes that this area here, it causes the area here is being reduced from the original area. The original area is roughly around this size, okay, roughly around this size as shown as when you look into my pointer here, okay. So originally your point 4 is here, so where I place my pointer, okay. So this area here is based on the reverse Carnot cycle. So for the ideal vapor compression cycle, the area is reduced to this. So that means your cooling effect or refrigerating effect has been reduced. Okay, so that is the limitation of the ideal vapor compression cycle. So this diagram, the schematic diagram, also have been changed. Okay, instead of using turbine, now we are using an expansion valve, which is a directional valve, one direction. There is no reverse flow. So during this expansion, irreversible expansion process, the enthalpy at point 3 would be equals to the enthalpy at state point 4 according to irreversible throttling process, which you have studied in your steady flow at steady flow devices, okay, which this process become irreversible for throttling anything that is involved in the expansion through a valve. Okay, so the evaporator, compressor, and condenser still remain the same, reversible, reversible, and reversible. But these three are reversible, and these become irreversible. And then the evaporator, the condenser will have to operate under the process of constant pressure. Please bear in mind, okay, please remember, yeah. So based on this TS diagram, we have our state point 2 here is dry vapor, dry saturated vapor at state point 2. It will be saturated liquid ammonia. And then state point 4 here will be the mixture of liquid and vapor, which also I call it as wet vapor, state point 4. And then state point 1, which is also wet vapor before it goes into the compressor. That is also the compressor inlet. But then when you look at this, there is a limitation, that is your point 1. Still need to modify. This one still needed, or still, okay, needed to be modified. Because point 1, inlet to compressor, compressor cannot deal with two-phase substance. That means liquid plus vapor. Compressor cannot deal with. Okay, so it only deals with vapor. So that is why it's called a vapor refrigerant compressor. So these are the data they have extracted earlier from the property table. Okay, with your Hg, Sg, Sf, and Hf with respect to the evaporator pressure and the condenser pressure. Okay, so we start with state point 1, but this time we are going to make use of enthalpy. Okay, we use enthalpy to measure how much work in, how much heat absorbs, how much heat rejects. Okay, so state point 2 here, which is dry saturated and at a pressure of 12.37 bar. I have stated here in rate, dry saturated vapor refrigerant at this pressure, 12.37 bar. So if I want to find the enthalpy H2 here, I will have to take the Hg at this pressure, that is at 12.37 bar, that is 1469.9. Then the S2 would be equals to the Sg at this pressure, which is 4.962. See here? Okay? Then state point 3, that is this. This is still at the pressure of 12.37 bar, which is, but now is saturated liquid refrigerant at this pressure, still at condenser pressure. Okay, so H3 would be equals to the HF because the saturated liquid is sitting on the saturated liquid line. So you take the HF, not the Hg this time. HF, okay, 332.8. Sorry, the HF, sorry. HF is 332.8, and then the SF is 1.235. Okay. Then state point 4, that is this. Remember, 3 to 4 is an irreversible expansion process or a throttling process. So according to a irreversible throttling process, the enthalpy is constant. Okay, so I have written here, irreversible expansion to 1.902 bar, that is this pressure here. That is where your point 4 is sitting. Okay, at the evaporator pressure of 1.902 bar, and is a saturated liquid vapor mixture, not saturated liquid, saturated liquid vapor mixture refrigerant. So H4 equals to H3, so it's equals to this 332.8. Then the last one is your state point 1. So state point 1, wet vapor, or this saturated liquid and vapor mixture at this pressure. Okay, so we know that state point 2, state point 1 is isentropic. So the entropy of state point 2, which we have found just now, okay, take this for S1 as well. take this S1 to be equals to this because it's isentropic. So S1, due to reversible isentropic process, S1 equals to S2. Okay, due to reversible isentropic process, S1 will be equals to S2. So S1 also will be equals to 4.962. But at your state point 1, which is at this pressure, your S is 5.623. Your SG is 5.623. You compare. We are looking at point 1, yeah? Evaporator pressure, so you look at this, not this. This will be at this upper line here. Now you look at this line here, which is 1.902. So you compare this value with this value. Why this value? Because your S1 equals S2, you take from here. So you compare, this is less than this. This value here is less than this value. So that means it's wet. So that means it's wet. So when it is wet or is a mixture of liquid and vapor, you have to find out its dryness fraction. So you use this S1, SF1, now, which is at 1.902 bar, everything at 1.902 bar, SF1, 0.368. SFG1, you take SG minus SF. Okay? SG minus SF. So you have your SFG for this at 1.902. So that is 5.623 SG minus 0.368 SF. So find out your dryness fraction. So you've got X1 is 0.874. Then only you go for your enthalpy. So H1 equals to HF1 plus X, which is the dryness fraction or the quality of the vapor, HFG1. This is not steam, yeah. We are not looking at H2O, yeah. We are looking at some other type of constituent or substance. So we call it as vapor. So this is the dryness fraction of the vapor at this pressure again, because you are referring to point 1. So at point 1 is 1.902 bar, the HF is 89.8. The HFG will be your HG minus HF. HG minus HF. So you take 1420 minus 89.8. So you got 1252.4. That is your H1. Okay, so once you have got H2, H3, H4, and H1, then we can go ahead. List down everything here in the table. I've got it, everything listed on the table, so it's easier for us to pick up the values when we do our calculation, especially during online, okay, studies. Okay, so that is why you can see every slide I have to put in the diagram, so it's easier for you to see and compare. So point 1, we have found out the dryness fraction, which is a wet vapor. Point 2, which is dry saturated vapor, I have found the enthalpy. And then saturated liquid H3, also I have got the enthalpy. And since 3 and 4 is irreversible expansion process, so they are equal. This is saturated liquid. This is not wet vapor. This is mixture of vapor and liquid. My mistake here again. So remember, RE is the refrigerating effect that is in the evaporator. RE is always measured based on the evaporator. You can straight away take H1 minus H4. Okay, so you got your RE 919.6 kilojoules per kg. Then your work in that is based on the compressor. Okay, you take H1 minus H2 or H2 minus H1. Take the greater value minus the smaller. So you compare. This is greater, this is smaller. So you take this minus this. H2 minus H1. So you got 217.4 kilojoules per kg. That is for your work in. Okay, so we don't have to find heat rejection. Yeah, heat rejection is when, if let's say for example, we want to find heat pump. Let's say we are looking forward for heat pump, then you include heat rejection. Otherwise, for refrigeration, no need to refer to heat rejection. Okay, unless otherwise stated in the question they want you to find. COP for refrigeration, RE over work in. So you got the COP is 4.23. 4.23. Okay, that's for the second part. Thank you. Stay safe.